our first part of the free response question asks us to draw a force diagram or a free body diagram of the ball when it is at 30 degrees, as shown in the diagram here. So before we start with drawing the free body diagram, let us first attempt to visualize the problem. So here I have a ball and a string of some length L. And what I'm going to do is, it's going to be in a horizontal position, as shown over here. And then I'm going to release it. The ball's going to fall down like this in a circular path. And it's going to reach some point, where, like over here, approximately, where the rope is going to make a 30-degree angle with the horizontal. And we need to find the free body diagram of the ball at this point. So let us think about some of the forces that are acting on the ball. So here we have our ball. And we know that there's going to be a weight force of mg pulling down on the ball. And if you look at our diagram, we see that the ball is also attached to a rope, which means that there must be a tension force which will pull on the ball. And that tension force is going to act along the rope. So our tension force is going to look somewhat like this. And this is our free body diagram. So part B of the question asks us to find the speed of the mass at point P. So whenever I see a question which asks us to find the speed of something in these sort of situations, I always think of energy. So we can see over here that at the beginning that our mass is going to have, it's not moving, so it's going to have zero kinetic energy. But it's at some height, and we can just take P as our reference point, or zero reference point. So M is going to be at some height. And for P, we see that it's going to be at a zero height, so it's going to have zero potential energy, but it's going to be moving, so it's going to have some kinetic energy. So let us try to find the vertical height through which the mass has dropped. So we can draw a line like this, and we can see that this triangle which we formed over here is a right angle triangle, and we know that this length, the hypotenuse of this triangle, is going to have a length of L. By trigonometry, when we use trigonometry, we see that this length, our vertical height, is going to be equal to L sine 30, which is going to be equal to L over 2. So now we can use our conservation of energy, which states that the change in potential energy plus the change in kinetic energy is going to be 0. So we see that the change in potential energy, remember we're taking this as our reference point, point P. So our initial potential energy is going to be mg into h, or in this case, mg into L over 2. And our final potential energy is going to be 0. So our change in potential energy is negative mg L over 2. Our change in kinetic energy, this initially had a kinetic energy of 0 because it wasn't moving. And at the end, it had a kinetic energy of half mv squared. So the change in kinetic energy is given by 1/2 mv squared. So we can add this on both the sides. So you get half mv squared is equal to mgl over 2. And since we're trying to find v, let us try to isolate it. So we can divide by 2 and multiply by 2 on both the sides. And we can cancel out these m's to get v squared is equal to gl. And finally, we can take the square root on both the sides to get that v will be the square root of g into L. For part C of this question, we need to determine the tension in the string. So before we begin, let us take a trip back to part A over here and look at our free body diagram. So we need to use this free body diagram to solve this question because this is a forces question. So let me redraw the diagram again. So here we have mg, and here we have t. Now it might be intuitive to split t into its components, but that's not going to help here. The reason is we know that this object is undergoing a circular motion, so it's probably best to resolve all the forces in the directions which are perpendicular to the radius of the circle and parallel to the radius of the circle. So what we will do is we will split mg up into its components. So we know that here's the horizontal, and this is 30 degrees. Since these two vectors are going to form a right angle, we know that this is going to become 60 degrees, and since these two also form a right angle, this is going to become 30 degrees. So this vector over here is going to have a magnitude of mg cosine 30, and this vector is going to have a magnitude of mg sine 30. So we know that our mass is going to be going in a circular path, and whenever an object moves in a circular path, there's always going to be a centripetal force, and that force is only going to be produced by other forces which act along the radius. So we can see that using Newton's second law, that T minus mg sine 30 is going to be producing a centripetal force of mv squared over r. I mean, in this case, that would be L. So sine 30 is half. So we write so T minus mg over 2. And we know from part B that v is going to be square root of gl. So v squared is going to be just gl. So we can split that in mgl over L. And our L's are going to cancel out. So we get T minus mg over 2 is equal to mg. Finally, solving for T, we get T is equal to 3 mg over 2, which is our final answer.